Thank you. Okay, yeah, so this is not about AlphaGo, and you can take it up with him. So this is joint work with my colleagues Daniel Paulin, EYT, Brendan O'Donoghue, and Arnaud. Okay, so the problem that I'm interested in these days, and the problem that we're going to talk about, is the sort of classical problem of optimization. So we're going to assume that someone gave us a differentiable function f, defined over a bunch of real parameters. And our goal is to find either the minimizing set of parameters or at least a locally minimizing set of parameters. So if you've implemented a neural net and trained it, then you've tried to solve this problem where x would be the weights of your neural net and f would be the loss function that you're trying to minimize. Okay, so if you're already not motivated, I want to spend a little bit of time describing why I think A, this is an important problem for machine learning, and B, it's actually underappreciated how big of a problem it is. So I think there's a really big imbalance in our machine learning pipeline at the moment. Most of the time as a practitioner is spent designing a model. So you think about your data, you think about the structure of the problem, you design a model that reflects that knowledge, and then you write tf.atom optimizer, and you go and you run with that. But at the end of the day, most of the success is actually determined by the optimizer, and you also know that if you've tried just running gradient descent instead of atom on your data set. And in fact, there's only really 10 optimizers that are shipped with TensorFlow as sort of standard, 5 of which I hadn't even recognized before because we very rarely use them. So I would say actually the bulk of the optimizers that we use are probably around 5. And so the sort of question of this talk is going to be, well, have we discovered all of the useful optimizers? And if not, how can we design new ones? Okay, so another motivating quote is from my friend Roger Gross, who's a professor at the University of Toronto, and he tweeted this out the other day. If there's any doubt that optimization is still a bottleneck for neural nets, consider how many architectural innovations were basically ways to get stochastic gradient descent to work better. Okay. Okay, so it turns out that optimization is a very unique field within computer science. And this goes to the question of, well, have we discovered all of the useful optimizers? In computer science, the theorists tend to be interested with the question of lower bounds, which is to say, do we know some fundamental limit in terms of how quickly our algorithms can solve the problems that we're interested in solving? And so in the 80s, some Russian scientists really delineated the computational complexity of optimization. And they did so by asking the question, okay, what is it about your function? What information about your function is the method exploiting? Is it just using the function values at certain points, in which case one would call that a zero order method? Is it also using derivatives at certain points, like gradient descent, in which case they would have called it a first order method? Or is it also using second derivatives at that point, and so on up the hierarchy? And it turns out that depending on the information that you use, you can delineate these lower bounds, and that these complexity classes are very well understood. Not only that, within months of them publishing this lower bound that says you can't go faster than a certain rate on this optimization problem, Nesterov famously matched it with his accelerated his accelerated gradient descent. And so at least for that class within that model, sort of resolved the question of whether there are any useful optimizers left to find. And before you come up to say, okay, yeah, that's all well and good, but I'm working on non-convex problems, so this doesn't really apply to me. Just want to remind you that non-convex problems actually include convex ones and more. So you're not really making your life easier, you're just making your life worse. So if we want to really start pushing the boundaries of what's possible with optimization, we should be very well aware of this theory and think not just within the hierarchy, but also laterally. And consider and be really clear about what information about our function we can exploit and how we can move that into our algorithms. Okay. So for neural networks, oh, sorry, I'll get to that in a sec. Right, so the central question here is, can we make a lateral move from this hierarchy? Instead of just using the gradients of our function, suppose we're given access to the gradients of another function. So this is going to be denoted throughout the talk as k. And k is going to be defined, again, over the same space, the same size of the space, the same number of parameters. And we're going to ask, OK, can we design algorithms that use both the gradient of our function and another function in order to speed up optimization? Obviously, we have to, at least theoretically, restrict the kind of k's we could choose, because we could cheat and choose one that returns the minimum in one step. So we can't just assume we get any k. But the whole name of the game of this talk is going to be, how can we design k to speed up optimization? And I'm going to sort of, throughout the talk, delineate exactly what that means. Of course, for neural nets, where we're usually just using gradients, we could also expand or do better by using second-order derivatives, and the theory tells us that that's possible. But that's usually expensive. Although, I should say, there are some really interesting attempts to do that in this family of algorithms under the sort of KFAC moniker, but I'm not going to talk about that today. OK, so this is the outline. First, I'm going to, let's see, turn this on. First, I'm going to develop a sort of simple tool for us to use to reason as we go through the talk, which is going to be understanding optimization algorithms without discretization error in a kind of continuous differential limit. Then we're going to look at simple gradient descent on one-dimensional examples, which are going to be power functions. And the reason we're doing this is that it's actually going to illustrate in a very, very, very simple framework the sort of deep results of computational complexity for convex functions in general. It's just going to reflect it. It's not the full theory. Then we're going to introduce these Hamiltonian descent methods, which we've introduced in a new paper on arXiv last week, again on the simple power examples. And that connection will be clear. And then I'll state some of the general results that we have on convex functions and conclude. So this work is just going to be about convex functions. Clearly, we're interested in going beyond that in later work. OK. So this is the basic gradient descent algorithm, which is actually the backbone of all of machine learning as we think about it today, at least deep learning, the deep learning slice. So we have our function f. We're going to start at some point in parameter space x naught. And at every iteration, we're going to take the previous point xk and add some constant multiple of the gradient evaluated at that point to get our next point. And so this in 2 dimension is kind of the picture. We're sitting somewhere on the level sets of this function, which you can think of these contour lines as kind of a topographic map of the function that we're trying to optimize, and we're trying to get to the star. We're at this blue point, and our gradient is going to point in the direction of steepest increase. That should have been a minus. And we're going to follow the minus some constant of the gradient to move downwards in the function. OK. And the goal of this subsection is to understand what happens as our parameter epsilon goes to 0. OK. So this is kind of what happens in pictures. For a relatively large step size, we have the following sequence of iterates in our space, and they approach the minimum. That's good. As we make the step size smaller, the iterates get closer and closer. And as it gets even smaller, they start to approximate what looks like a continuous curve in space. And in fact, you can show under some regularity conditions on our function f that they approach a differentiable curve, which we're going to denote by x sub t. So t is now a parameter that denotes time. It's a continuous parameter. So this is a function from time into some point in space. And that this curve satisfies this differential equation. And just the way to read that is to say that the derivative of the curve in time at a specific point is given by minus the gradient of f at that point itself. And so if someone were to say, aha, I have a solution to this differential equation, it would have to be the case that this is satisfied for every time t. And that it starts at some point x naught. OK, so why did we bother with that? Well, it turns out that continuous systems tend to be much easier to study mathematically, and that they can really simplify our analysis and illuminate kind of fundamental properties of what's going on. And we're going to show that in the power function case. But here's a very, very simple example. OK, so we were trying to minimize our function. And I gave you this algorithm, and I didn't convince you at all that it made any sense. to do that. So here is the kind of one-line proof that convinces you that it's a reasonable thing to do. Okay, so if we ask, what is the derivative of the function value evaluated at that curve in time at some point t? Well, you just use the chain rule. So you get this inner product between the gradient of the function and the derivative of the curve at that point in time, which is itself minus the gradient. And so you get that it is the minus squared norm of the derivative of the function at that point, which is always less than or equal to 0. If you know a little bit of calculus, that means that this function f of xt along the curve is always non-increasing. So we can't move upwards, we're only moving downwards in the function. And in continuous time, this is a one-line proof, but if it's not continuous, then you have to be a little more careful. So this allows us to kind of understand fundamental properties quickly and design algorithms. Okay. So, right. Now with this new fancy little tool, we're going to move on to think about how gradient descent behaves on simple power functions. And so we're going to think about a function which is just in one dimension, for one-dimensional parameter x, the absolute value of x to the power b divided by b, where b is strictly bigger than 1. And the reason we're going to do this is that we're going to learn a lot about how gradient descent behaves on actually generic functions. And I'll talk about that later, but this is a sort of nice little sandbox for us to understand what affects the performance of gradient descent. Okay, so this is what these functions look like. If b is 2, we get quadratics. If b is bigger than 2, then we get functions that are growing very, very fast, far away from 0, and are very, very flat near 0. For b less than 2, we get functions that are very peaked at 0 and very flat, far away from 0. Okay, and then the gradient descent system in continuous time that we're studying turns into this. And we're going to assume that we started somewhere that wasn't 0 itself, because if we start at 0, we just stay there. So that's not a particularly interesting case. And we're only going to think about time as moving forward and not backwards. Okay. So it turns out you can show, and I've sort of omitted this in the slides because it's not super interesting to go through, that the function value at the curve for b less than or equal to 2 can be upper bounded by an exponential that is decreasing in time with a rate that depends on your initial position if b is strictly less than 2, or with a rate that is 1 if b is equal to 2, times the initial function value where you started. Actually, for b strictly less than 2, it's even better than that. It's not even a constant rate. You can show that it's actually an increasing rate as it gets closer and closer to the minimum. For b strictly bigger than 2, you can show that these functions, the function value evaluated at a point on the curve grows like 1 over t to the power b over b minus 2. Okay, that is just a bunch of symbols. It's not really clear what that feels like. So I've plotted here what those values look like over time. Okay, so this is time. Each colored curve is the log of the function value along that point, along the curve. I'm looking at b 4/3, b2, and b4. So just to like really drive the point home, at halfway through our simulation here, we're at e to the minus 20 for b2, but we're at e to the minus 5 for b4. That means that this is e to the minus 15 smaller than on the path along for for b4. That's a lot smaller. Okay, just to really drive that point home. This is the function value for b 4/3. So this is even better than b equals 2. So in log space, having something that contracts at a rate 1 over t to some power is logarithmic. If it's exponential, then it's like a linear line in log space. I just really want to drive home that these are not sort of arbitrary distinctions. There's quite a profound difference in the kind of convergence rates. Okay, so what is the kind of summary, the diagram of what we've shown so far? What we've shown so far is that for this system, exponential convergence in continuous time happens if and only if b is less than or equal to 2. For any b bigger than 2, we have sub-exponential convergence, which is slow. Okay. Okay, that's all well and good, you say, but like we can't actually really use these continuous time methods in practice, so what happens when we discretize? Oh, by the way, because these systems are converging slowly for b bigger than 2 in continuous time, it's very unlikely, unless you get extremely lucky with a choice of initialization and step size, that their discretized variants converge quickly. And you can show that, but I'm not going to worry about that. So let's just think about what happens when we discretize the system for b less than or equal to 2 and see if we can preserve this kind of exponential convergence in discrete time. Okay. So let's take a step size less than 1. The iterates of gradient descent can be described by this equation. So you're at a point xk, and you multiply it by 1 minus epsilon times this. Okay. It turns out that for b strictly less than 2, this diverges for most of the trajectories. Okay, so to give you a little bit of intuition, I've plotted here xk on the x-axis. And on the y-axis, I have the dotted line representing equality. So anything below this is smaller than xk, the magnitude of xk. Anything above this is bigger than the magnitude of xk. The straight line, is the magnitude of xk plus 1 according to this equation. What we want to do is to drive our system towards 0. As the magnitude of xk gets smaller, we're actually mapping it to points with higher magnitude, which means that if we get into this regime, we'll actually be pushed backwards and then forwards and backwards and forwards, and so we'll converge to somewhere right around where these things intersect. Okay. And just if you didn't believe me, here is the simulation. So this is the same systems that we were looking at before, but now in discrete time. And we've taken a step size of 1/2. And we see that b equals 2 still converges exponentially fast. Sorry, by the way, notice if b is 2, then this is just a constant 1, regardless of where you are. So this, for b equals 2, we still converge exponentially quickly. For b4, well, we're still converging slowly, but we're not surprised. But for b4 thirds, we don't converge at all, and we just hit this sort of dead zone. Okay. So this is kind of weird. We had all these possible b's, and only one of them allows us to converge exponentially quickly with a discrete method, and that's b is equal to 2. So this kind of raises the question, wait, is 2 a special number in some sense? Okay. Well, 2 is very special for lots of reasons, but it's particularly special in this case because if you look at the updates and you look at this little bit, you realize that this is actually the second derivative of the function. For b, and the only case where this second derivative is a constant is b is equal to 2. For b greater than 2, the second derivative is collapsing when you get close to 0. For b strictly less than 2, it's exploding when you get near 0. And so you can think about the second derivative in this case as annealing the learning rate as you get closer and closer to the minimum. In this case, it forces you to slow down. In this case, it stops you from converging. And only in this case can you go quickly. Okay. Okay, so you might be saying like, oh, well, that's all well and good, but you only looked at one algorithm. I can come up with clever tricks for changing the learning rate in order to counteract that, right? Suppose for the b is less than equal to less than 2 case, well, I could make my learning rate smaller as I go, in which case I could counteract that effect that we just noticed. So this sort of poses the question, well, can we come up with like a generic theory that describes whether we're able to go as quickly as we would like for a generic function. And this is the topic of the lower bounds in convex optimization. So just to remind you, or if you haven't seen it before, a function f is convex if it satisfies this inequality for any 2 points x and y in its domain. And this has a quite sort of intuitive interpretation. So this is the function value f of x, let's say, which I've plotted here in black. This, as a function of x, is a linear function. And so what this is saying, essentially, is that you can lower bound the convex function anywhere by this linear plane, or by a linear plane. So every linear lower bound totally lower bounds the function, uniformly across space. Okay. There are two important concepts for optimization, or sort of fast exponential optimization for convex functions. And we'll get to what they mean, but they are respectively the notion of strong convexity and smoothness. And this is not the sort of proper definition, but I think it's the most intuitive, so it's what we're going to run with. For functions that have two derivatives, so twice differentiable functions, these properties are equivalent to there existing a constant mu, such that the eigenvalues of the Hessian are everywhere lower bounded by mu, and that the eigenvalues of the Hessian are everywhere upper bounded by L. And the kind of key take-home that you should be thinking here is these conditions are equivalent to saying that the second derivatives are bounded everywhere between two positive constants. And if you go back to F space and not just its derivatives, this means that F can be bounded by quadratics, not just linear lines. Okay, and in pictures, it's the following. So this would be, let's say, the second derivative of a function. Well, it can oscillate, but the condition of strong convexity says that there has to be a positive lower bound everywhere mu. Smoothness would be the existence of a positive upper bound everywhere, L. And this is bounding that function by quadratics. Okay, this should be reminding you of the b equals 2 case, and that's not an accident. Okay, so as I mentioned, there are weaker definitions of smoothness and strong convexity. And those weaker definitions actually turn out to be critical in high dimensions. And so I should mention that this lower bound theory actually only really properly lives in the context of high dimensions. For one-dimensional functions, you can do all kinds of wacky things, but for high-dimensional functions, it's kind of asymptotic arguments. And so if we know that our function, our convex function, is smooth and strongly convex, then most first-order methods, which are, just to remind you, methods that only ask for gradients of your function and function values, you can usually show that they converge exponentially quickly. On the other hand, so these are the sort of famous lower bound results of Nemirovsky and Newton. For any first-order method, no matter how clever you think you are, if all you use are gradients and function values, then there always exists a smooth convex function f and a non-smooth, strongly convex function f on which convergence is slow. For example, for smooth convex functions, you can show that the difference of the function values is lower bounded by 1 over k squared. In other words, there exists a convex function for any method that forces you to go at that rate, which, as we discussed, was slow. So this kind of gives us an answer which we alluded to in the power function special case, which is that actually it seems like 2 is a special number for convex optimization. Okay, so this is really interesting because it sort of mirrors the intuitions we built on power functions. And it suggests to us that methods that only use the gradient of our function are very unlikely to change that picture. Now you have to be careful about what assumptions these sorts of lower bounds make and the exact order of quantifiers, and there's some subtlety there. But the rough take home is that if you're only using gradients of the function, you should be very skeptical if someone says, oh, I can go exponentially fast for all convex functions. Okay, so let's return to the sort of premise of the whole talk, which is that, okay, suppose we have more than just gradients. Suppose we have access to a second function k, and we can evaluate its gradients anywhere in space. Now we're going to talk about a method that sneaks information about f into k in a way that apparently violates, it doesn't violate, obviously, there's no magic, but it apparently violates those lower bounds. And the idea is that we're actually using this to encode more information about f than just its gradients. Okay. And these are the methods that we're calling Hamiltonian descent methods. Okay, so to motivate these, what are we doing? Oh, I'm going really quickly. Okay, great. Actually, are there any questions? No, okay, that's fine. Okay, so to motivate these methods, I'm going to talk about probably what is actually the most popular, or was before the atom optimizer and RMS prop for neural networks, which we call gradient descent with momentum. In the optimization community, it's called Poljac's heavy ball method because Poljak introduced it in 1964. The basic idea here is that imagine you're in sort of a long, narrow valley. You might end up with a gradient, and you're sort of jumping between each side, and the gradient is pointing back to the other side. What you really want to do is capture the concept that there is sort of a persistent gradient in one direction, despite in another direction the gradient changing quickly. And so the idea behind this method is to add sort of a persistence of motion in the dynamics. And how do you do that? So to do that, you introduce a second variable, p, here pk, and p is going to accumulate the gradients of your function. So at every iteration, you evaluate the gradient at the point that you're at, and you add it to the previous value of p, of the previous value of p, and so you can see that over time, p is going to sort of store the persistent components of the gradient of f, and sort of the ones that cancel each other will cancel out over time. And then our position update is just to say, well, move in the direction of p instead of just the gradient itself. Okay, and in pictures, this is what it looks like. So if you remember, gradient descent just sort of did this sort of slow little, it sort of sloped gently into the minimum. Gradient descent with momentum tends, anyway, to oscillate because it has that persistent motion. Okay, and then we're going to do this now age-old trick of letting the step size go to 0 so we can kind of understand the fundamental properties of the system. And if you let the step size of this go to 0, you end up getting this bipartite system. So the derivative of the curve of your position at a point at time t is exactly the value of the momentum. And the change in the momentum at time t is the minus gradient of your function minus a contribution from its value at that point. Okay. So the idea here is, this is going to look like I'm just pulling it out of thin air because I didn't want to go into too many details here. But the idea is that instead of a linear update to your position, we're going to see if we can use the gradient of our function k in order to make a nonlinear update. And we're going to study how we can condition k so that this whole system converges exponentially fast. And notice that this is the same system as the heavy ball if we had happened to choose a quadratic for k. And if you're noticing a lot of 2's, that's not an accident either. Okay. Okay, the reason we're calling this Hamiltonian descent, there's all sorts of connections to physics, which we talk about in the paper, but just a sort of a pithy little thing. In physics and in geometry, these are studied, and they're called conformal Hamiltonian systems. And in particular, the function k is known in physics as the kinetic energy. And so that's the name I'm going to use from here on in. Okay, so let's go back to the power functions because everything's easier to understand there. Okay, so just, right, so we're going to again take f in this family where it's the absolute value of x to some power b, which is strictly bigger than 1. We're going to take k from the same family, but let it possibly have a different power, a. Okay, so how do we even try to sort of visualize what's happening in the systems? Okay, so what we're going to do is we're going to split the vector field that describes the dynamics of that differential equation into two components. One is going to be the gradient of k, which is here, and minus the gradient of f, which is here. And the second is going to be a field which is 0 for the derivative of the position and minus gamma p sub t for the derivative of the momentum. If we look at these kinds of systems, in physics, these are called just Hamiltonian systems. And so what I'm plotting here is for every position x and every momentum p, because these are in one dimension, they're jointly in two dimensions, the direction of the arrow that's pointing is you start at some pair xp and you point in the direction of that vector field. And so you can imagine curves, solutions of a differential equation that don't have this component will just move in circles following the arrows of this vector field. This component of the vector field has no effect on the position because it's 0, but has a sort of downward effect on the momentum variable. And so if we add these two together, we have now arrows that descend towards a point. And this is what a solution looks like in that joint space of, actually these are two solutions, of parameter positions x and momentums p. So this light blue line is one solution, the dark blue line is another. If nothing else, we've made some pretty spirals. Okay. Right. Okay. So what's going to follow is like a super rough physicist explanation of how you should choose A. Okay, so what can go wrong for this system? When is this system going to slow down? At least informally, the worst case that could happen is if this is a small value, so x isn't changing a lot, and pt times gamma has opposite sign from the gradient of f, but has a balancing magnitude, so that in other words, this joint thing is also small. That's like the worst case. So when the change in your momentum is small and the change in your position is small. When that's true, when these two terms have balancing magnitudes, then we can think of them as sort of roughly being just the gradient of f at that point times some very, very small constant. And so the change in the momentum at that point of time is going to be roughly the gradient of f evaluated at the gradient of k times a little tiny step size, which is going to look sort of like this. Okay, so this is sort of what failure mode looks like. This is optimizing x to the power 4 with a quadratic kinetic energy. And you get basically, it's hard to visualize sort of what the clock of time is here, but basically this has slowed to a halt and you want to get here. So we don't have that nice spiral where energy is sort of being exchanged between the momentum and the position, but you hit this region where both of them are slow. And this is happening in a kind of different direction, but it's the same principle. Okay, so if we want to escape that region, we want our kinetic energy to be going fast at that point. Okay, so let's look at what the change in the kinetic energy is roughly at that point. In this worst case scenario, we're going to have sort of the partial derivative of k and p times the derivative of p and t. And if you just sort of do the math, it looks roughly like this. To escape this region or to have sort of fast convergence, what we want locally is for such an inequality to hold. At the very least, for very small p's, we want such an inequality to hold. Yeah, that might not be intuitively obvious. It probably isn't. But anyway, you're just going to have to trust me on this. If you do know a little bit about these things, this is so that you could use something like what's called Gronwall's inequality. Anyway. Okay. Oh, if you've taken differential equations and this was an equality, it would be pretty clear that this is something that's converging exponentially. Okay. Anyway, if we want this kind of thing to be satisfied locally for very small p's, this implies that we ought to take this power to be less than 1. Otherwise, for very small p's, it's not possible to satisfy this inequality. Or in other words, we want 1 over a plus 1 over b to be bigger than or equal to 1. Okay, and in fact, and we have this in the paper, you can show that this intuition holds. And you can show, so in the gradient descent case, we just had a line. But now because we have B and A, we have a two-dimensional plane whose regions we want to delineate. You can show that exponential convergence happens only if 1 over A plus 1 over B is strictly bigger than 1. In other words, you have a region up here where, unfortunately, the optimization community calls exponential convergence linear. So just ignore that. It was the biggest mistake. Anyway, okay. So up here you have sub-exponential convergence. And in this area you have exponential convergence. Notice, by the way, in the gradient descent case, we were just sitting on this little line here. Which means, at least in continuous time, we now have a system that can converge exponentially fast for powers bigger than 2. Okay, here's sort of another way to see it, I guess, which is that you're trying to optimize this function, and let's say B is big. Then you have very flat area here near 0 and very steep area up here. If you're very far away from 0, you want the change in your position to be relatively small because the gradients are going to be massive, so you want to sort of dampen that. If you're very close to 0, the gradients are going to be tiny, so you want to amplify it. And if you ask, well, what is the kinetic energy that exactly balances those two concerns? Well, it's the one whose power is, satisfies this equality. 1 over A plus 1 over B is equal to 1. If you've taken math and you're noticing something called Holder's inequality or the Fenchel-Young inequality, that is absolutely not an accident. Okay, so that's all in continuous time, but of course that's not what we can implement. So we're interested in studying discretizations. In the paper, we provide 2, which are suitable for different cases. I'm not going to belabor this, but basically we have one case for B greater than or equal to 2, one case for B less than or equal to 2. And again, as with gradient descent, we're going to lose something when we discretize. Similarly to gradient descent, we're really only going to be able to capture the boundary of a region. So what we show is that our first explicit method that I put it up there converges exponentially fast in the region B is bigger than or equal to 2 so long as A is chosen to satisfy this equality. And the second explicit method converges exponentially fast so long as, for B less than or equal to 2 so long as A satisfies the same equality. So just to drive it home, where before we were sitting on the dotted line with only one point where you can get exponential convergence, we now have this entire line of BA pairs where you can get exponential convergence. Okay, right, so not every function is a simple power function in one dimension. Okay, so in the full version of the paper, we consider the finite dimensional case. We provide generic conditions on the match between a convex function f and a strictly convex function k that doesn't assume that they're power functions necessarily. So we just provide sort of absolutely generic conditions that say this is how you should be pairing these things that ensure exponential convergence both in continuous time and discrete time. And in a sort of analogy to the discussions, you're always restricting the class of functions as you move towards discrete time. You have to assume more and more about your functions. The key condition, which is required for exponential convergence in continuous time, is this, which looks pretty awful. But if you've taken any convex analysis, you might recognize this guy, which is known as the convex conjugate. In general, and this is a specific convex conjugate of some centered version of the function that isn't sitting at 0. This is usually very hard to compute, and its gradients are usually very hard to compute. So requiring that k was exactly, requiring that k was exactly the convex conjugate would be ill-advised and not very useful. So we show that in fact the only thing that you need is that it upper bounds some constant times the maximum of this conjugate at p and at minus p. And in particular, if you can lower bound the centered version of the function by a symmetric function whose conjugate you can compute, you're able to satisfy this. We study a family of kinetic energies that have power growth, but that power growth might be distinct whether you're near infinity or near zero. So instead of having just the same power everywhere, as in our example, we study a family that can grow like some power far away from zero and some other power near zero. And for each of these, we provide conditions on the convex function that ensures exponential convergence. And just to drive the home point, these conditions are analogous to strong convexity and smoothness, which we more or less up to this point felt were necessary, although not, I don't want to say something that strong, but are very, very important. So these extend those conditions, basically. And in specifically the case that you choose A and little a, big A and little a to be 2, you essentially recover the conditions of strong convexity and smoothness. So you could have functions that are ridiculously flat, ridiculously fast, sort of flat everywhere, or some combination. Okay, and in pictures, what this means is that where previously we really relied on these notions of strong convexity and smoothness, where we bounded the second derivative between two constants, we can now cope with second derivatives that explode and that collapse near the minimum, so long as we're sort of able to bound them by power growth of the appropriate kind. So in a sense, we've generalized gradient descent to cope with second derivatives that are exploding or vanishing near the minimum or at infinity. Okay, and this is sort of what the picture looks like in a sense. This function is a function that looks like x to the power 4, but is in 2 dimensions and tilted. These are the iterates of the different algorithms. So in light blue is gradient descent. In medium blue is the classical momentum algorithm. And in dark blue is the Hamiltonian descent, provided that you picked the right kinetic energy for this problem. Okay, and just one last thing, which is that we consider a special case of these power kinetic energies that we introduce, which are very closely related to the relativistic kinetic energy of physics in the sort of Minkowski interpretation, and they look like the following. And you don't have to worry too much about it, except I want to note that this, up to some, dimensionality issues, looks a lot like the position update of RMS prop and atom and eta grad. And we show in the paper that this choice of the kinetic energy is a generically good choice for functions that look quadratic near their minimum but have arbitrarily fast power growth near infinity. And in particular, it's robust to initialization. So you could start at a point very, very, very far from the minimum with absurdly high gradients and converge with a fixed step size that doesn't depend on position, and that this naturally anneals you to speed up as you get closer to the minimum. Yeah. So even though we haven't studied neural nets yet, this is sort of pointing us in the direction of there might be some empirical confirmation that such ideas are useful in deep nets. Okay, so just to conclude. In this work, we extended the class of convex functions on which exponential convergence is achievable using just gradients. There wasn't any magic because we introduced a second first-order oracle through which we snuck information about our function, which is essentially of second-order nature. But we only computationally have to use the gradient of the kinetic energy. This, I think, for me anyway, raises a lot of interesting questions, which is like, well, from a theoretical perspective, are there meaningful lower bounds in this context where you assume you have the gradients of two functions? And I've sort of maybe hidden this a little bit, but that the biggest limitation for these things is that you require some knowledge about F in order to design K. And so I think it would be quite interesting to see whether you could develop adaptive methods that maybe don't require that. And then finally, I just want to thank my collaborators, and in particular, Daniel, who's a joint co-author who, yeah. great to work with him. So.
Thank you. Are there any questions?
So you mentioned that you choose this K to encode information about F, but then you end the presentation with saying here's a generically good K.
Oh, okay, yeah, sorry. Okay, sorry. Yeah, right. Okay, let's be more clear. So, how to describe this? Okay, so for this family, you have two choices. You have the choice of big A and of little a. There's kind of an asymmetry in terms of which one is more important to get right. Little a is crucial to get right because that's what describes the behavior like at infinity as your system is converging. So little a has to exactly match the behavior near the minimum of your function. That might sound like really harsh, but just remember that like gradient descent with momentum picks 2 for both of those. So you could just pick 2 for little a, which would basically say that you're assuming that near the minimum your function looks like a quadratic. So if you think that's a generically good choice, then you should pick little a to be 2. But you still have this free parameter of big A. And that is much less critical. And so we actually describe in the paper so that you don't actually have to know exactly what the corresponding big B near infinity of your function is. And instead, it's encoded. Yeah, it's a little bit more complicated. But essentially, this alpha parameter here encodes how bad of an approximation you have. And this anneals over time. So in other words, this gets better over time. And so if you don't match the behavior at infinity, this is no longer a constant, but it is instead a function that is improving over time. And so you can capture the underestimation through this alpha, and which is exactly sort of what describes this, where we've chosen, maybe I should have written this, but this is choosing little a to be 2 and big A to be 1, which is sort of a generically good choice for very fast-growing functions, far away from the minimum. Okay.
Another question?
Yes?
Does anything change with noisy grades?
Yeah, that's a very good question. Yeah, we started looking into this. Obviously, everything changes. And this is the obvious follow-on work, which we haven't, I don't want to say too much because I don't think we have a good understanding yet. But given that there might be some relation to RMS proper atom, it suggests that maybe it's not the end of the world because those are both implemented in very noisy environments. So, yeah.
You already touched upon this a little bit, but of course for neural nets you don't generally know what the loss landscape looks like.
Yeah.
What are your thoughts on how useful this would be, or
Yeah.
if it's similar to, or there's some examples that work that might be similar?
Yeah, I mean, this is another good question. I think basically, this work was fairly theoretical, and it's like, okay, suppose you knew all these things about your function, how would you design K? And I think that kind of is interesting, especially from the perspective of a practitioner who has time and is a simple enough function that they can kind of prove things about it. But I think there's another part of this work that I haven't done, which is really important to do, which I'm hoping to do, which is this kind of like experimental exploration. So if you just were to think about K as a free parameter that you can fiddle with, I think there's a lot to try out on neural nets. The only positive indication I have, and some very, very preliminary experiments, is just that this relationship with algorithms that exist already. But beyond that, I'm not sure if we have enough knowledge to actually, I'm fairly certain we don't have enough knowledge to design these things today for neural nets. There is some work that tries to sort of understand the properties of the second derivatives of neural nets, which would be critical for understanding how to design K, which I think is interesting, but I think this is sort of part of a bigger research agenda. And yeah, I don't think it's at all resolved.
Yes.
Yeah.
So there's been some work on optimizer search. It's like literally search a space of update formulas and try to find the best one. And I think, if I remember correctly, there was no big breakthrough, even with a lot of computation. So I'm wondering if you've looked at that and considered, taking K as the thing you're optimizing over, seeing if that goes somewhere.
Yeah, so this is definitely something I want to do. I mean, yeah, this is the Google approach, which is like just throw a lot of compute at the problem and see what happens. But I think, yeah, so one of the things I'd really like to do, which I think would be a really cool project, like an empirical project, would be, say, so we have relatively light restrictions on k, like it has to be strictly convex and a minimum at 0 and differentiable. So you could imagine defining a kind of grammar over those functions and searching over the space of those functions to see if you discover anything. I think it could be really cool. Yeah, I want to try that. Yeah.
I got a question.
Yeah.
Could you actually have k being a function that you're learning instead of just making the grammar?
Yeah, I mean, you could parameterize it. You could do a learning to learn by Hamiltonian descent or something. Yeah, so as long as, I mean, you could do crazy things and just have k not even be convex and just see what the heck happens. I haven't tried that. But at the very least, not that theory matters anymore, but at the very least, you would like that it be convex. So you'd have to sort of try to stay in that space. But I suspect that it's actually, yeah, I suspect that it would be worse if it wasn't, I have not thought carefully about that. I think you'd break a lot if it wasn't convex. But yeah.
Other questions? All right, let's thank Chris again.
Thank you.
And see you around.